All right, so continuing on in our review of inductors, I think it's important to take a look at the IV or the current voltage relationship for inductors. Of course, we know that the voltage across an inductor, so if I were to draw an inductor here, we're talking about the voltage across the inductor, VL, and we're saying that that voltage is basically equal to, and if I call this IL of T, we're saying that the voltage across the inductor is proportional to the rate of change of the current through the inductor, okay? And so there's a couple of implications of this. The first one is that the current cannot change instantaneously through the inductor. An instantaneous change means that it takes zero time, right? So dt here would have to go to zero. If dt goes to zero, then this whole term goes to infinity, because if I take my denominator to zero, I'm dividing by zero. That implies that I would have an infinite voltage, and since I cannot get an infinite voltage, we know that the current through an inductor cannot change instantaneously based on this equation here. Another implication of this equation here is that the current in an inductor, basically this is more practical for AC circuits, the current in an inductor lags the voltage by 90 degrees for sinusoidal steady state. Okay, maybe we didn't talk about this directly, but this is an important concept here. For inductors, capacitors, it's the opposite. The voltage lags the current by 90 degrees. And so what does that mean? Let me just draw a little plot here. So if I'm plotting, say I'm plotting voltage in blue across the inductor sinusoidally, I know that my current lags the voltage by 90 degrees. So, and I can see that from the equation here, that VL is equal to L di dt. So at this point, my voltage is at a maximum, right? My voltage is at a maximum. So because my voltage is at a maximum, I know that that means that my di dt, the slope of my current, should also be at a maximum. So that would be the point where the slope is at the absolute highest, right there. Then, when my voltage is zero, that means that my di dt should be zero, so my slope there should be zero. So that's right where this current waveform hits its peak and has zero slope, right? Next time around, I come to this point where my VL, my voltage, is at a negative maximum, basically a minimum, which means that's where my slope of my current should also be at a negative minimum. And then here, I hit zero slope. And so that's where my slope, or sorry, zero for my voltage, so my slope of my current should be zero. And so if I were to keep drawing this with this same pattern, I get this waveform, right there. I get this waveform for my current through my inductor in the red, which is 90 degrees phase shifted, lagging by 90 degrees from the voltage. Okay, and so that's derived straight from this expression. We can see that that basically is just showing us that the voltage is just 90 degrees, sorry, the current is 90 degrees behind the voltage because the voltage is a sinusoid, and the current, if I were to take the derivative of this current with respect to time, I would get a sine wave. So this current right here is a time shifted or an inverted cosine wave. And so if you were to do the calculus, you would see that this, this works out. Okay, but just wanted to make comments on that. That's the sort of how we can show that the current lags the voltage by 90 degrees through an inductor always. That will always be the case if you're looking specifically at the voltage across an inductor and the current through it. And this is just important because this describes the IV relationship of the inductor. In the next slide here, I'm talking about the impedance of the inductor, which we should be really familiar with by now. Basically showing us that the impedance of the inductor is proportional to the frequency that we're operating at. It's also proportional to the inductance. So larger inductors have larger impedance at the same frequency. And if we are using the same inductors at two different frequencies, the one at higher frequency has more impedance, okay? And so what this is only important because when we get into mutual inductance, which we're going to get into, you're going to see the inductance pop up in this form. And we're going to need to recognize that, but I think that you're plenty confident with what the impedance of an inductor is versus, of course, a capacitor, which is 1 over j omega c. Right, that's the impedance of the capacitor. And basically what it means for the inductor's impedance to be proportional to frequency is that as I increase frequency, if I were to plot the impedance of the inductor, that impedance increases as frequency increases, right? And it's linear, okay? So I'm gonna go ahead and end this video. And in the next video, we're gonna get right into magnetic coupling. I feel like I've done just a brief little review of inductors. Obviously, I'm kind of just going fast because there's a lot to cover in this module, so I don't want to spend too much time on 220 stuff. This is all old news, hopefully, but if you have any questions, obviously feel free to let me know. I'm going to go ahead and wrap up this video, and we'll see you guys in the next video where we're going to start talking about magnetic coupling.